Hello, today I'd like to share our project on model-free, cyber-resilient coordinated inverter control in a microgrid. I'm Caroline Larsen. I graduated with a Bachelor's of Science in Electrical Engineering from Virginia Tech in 2024, and I'm currently pursuing an MS in Electrical Engineering. My research interest includes the cybersecurity of power systems, protection in inverter-dominated microgrids, and real-time simulation. In this presentation, I'll first give the introduction to the project and an overview of its contributions. I'll then give background on coordinated inverter control, long short-term memory, and bidirectional long short-term memory. Next, I'll give an overview of the study system that we used to test cyber attacks and our proposed detection and mitigation method. I'll then give an overview of the detection and mitigation method, and then I'll give the performance evaluation of our method. Lastly, I'll move to the conclusion. Inverter-based resources introduce new challenges in the power system, and new techniques are needed to improve the control of installed IBRs without having to access their internal control parameters. This is because IBRs that have already been installed in the power system are often black boxes or gray boxes, and their internal parameters cannot be modified. Many techniques use communication. One example is coordinated setpoint automatic adjustment with correction enabled, or C-space. This method improves the dynamic response of the entire power system, but it also exposes it to cyber attacks. Attackers can compromise communication networks of the power system to cause voltage and frequency instability. In 2023 alone, the U.S. Department of Energy reported 6 disturbances to the power system caused by cyber attacks. A famous example of a cyber attack is the 2020 SolarWinds attack, in which attackers used compromised software to access the local networks of customers, including electrical utilities. This shows that attacks can even happen if on networks that are not connected to the internet. One report found that 25% of utilities were exposed to the SolarWinds attack, and a 2016 attack caused widespread outages in the Ukrainian power system. This shows that cyber attacks in the power system are a growing issue. An important method to study the cybersecurity of the power system is simulating the power system with its communication network. The best way to do this is with a hardware-based test bed because it has the highest accuracy and can simulate the power system alongside actual communication hardware. However, real-time power system simulators such as RTDS are expensive. An alternative option is to use a network-in-the-loop test bed, which combines software-based power system simulation with hardware communication devices to provide high accuracy and at low cost. So in this work, we study the impact of various types of cyber attacks, including false data injection or FDI attacks, and denial of service or DOS attacks, on the coordinated control of grid-following inverters in 2 isolated local area networks on a microgrid. Our method is model-free and uses local measurements. It incorporates a long short-term memory-based method to detect attacks in the power system, and a bidirectional LSTM-based method mitigates these attacks. Our method is able to prevent voltage and frequency violation in real time, and it is also robust against grid transients such as faults. Lastly, we develop a testbed which uses PSCAD simulation and a physical network switch to conduct man-in-the-middle attacks and test the feasibility of our proposed method. So here, this diagram shows an example of coordinated inverter control. Setpoint automatic adjustment with correction enabled, or space, improves the transient response of an IBR by modifying the input set points to the IBR, and coordinated space further improves the response by using error values that have been communicated between IBRs. However, in a GFL IBR, the values that are communicated can be falsified, and this can cause voltage and frequency violations on the output of the IBR. As you can see in this diagram, each IBR receives a real power set point and a reactive power set point, and with C-space, these are modified using the error values received from 2 other IBRs in the local network. And this just shows the algorithm in more detail. As you can see from the modified values at the bottom, the set point is adjusted based on the communicated error values from the 2 other IBRs. One method for detecting attacks and time series data is long short-term memory, or LSTM. This is a type of recurrent neural network, and it's good at learning long-term patterns. It uses a hidden layer of cells to process the input data, Each cell incorporates the previous solid state T-1, the previous output HT-1, and the current input XT to produce an output for the current time step T. And this just shows the diagram of the internals of an LSTM unit. Bidirectional LSTM modifies traditional LSTM by combining two LSTM layers. The first layer processes the input sequence normally. The second layer processes the same sequence in reverse. The two outputs are then merged, and this can outperform LSTM for many tasks that involve more complex sequence prediction. This shows the diagram of our study system. It's the Seagray 14-bus North American distribution system modeled in PSCAD. It has 8 IBRs, 2 of which are grid forming and 6 of which are grid following. And the 6 GFL IBRs communicate in 2 local area networks. IBRs 1, 2, and 4 exchange data in local area network 1. IBRs 12, 13, and 14 exchange data in area 2. Our detection method is implemented at the remote terminal unit level. Each IBR has its own system for detecting real and falsified real and reactive power error inputs to its controller. This system is an LSTM model that has been trained on local measurements. These are the real power output, the reactive power output, the voltage and current of the IBR, as well as the 4 error signals received from the 2 other IBRs in the network. On each time step, the LSTM predicts either 0 for no attack or 1 for an attack. This diagram shows the data exchange between the 3 IBRs in more detail. As you can see, an attacker can falsify the error values sent to the other IBRs, but with the detection and mitigation method, these are corrected before they can reach the other IBRs. To train our LSTM model, we created a dataset using the PSCAD automation library, and we collected several cases, including grid transients and FDI attacks. Grid transients cases include load changes, set point changes, and faults, and FDI attacks include step attacks and ramp attacks. To train our model, we split the dataset 70-30 into training and validation data. After extensive hyperparameter tuning, the models with the highest performance across all case types were selected. We selected models that had high performance but had not yet been overfit. Our mitigation method is similar to the detection method. It operates at the RTU level, and each model is a BIOS TM, which is trained on local measurements, including the real power, reactive power, voltage, current, and input error signals. But instead of predicting an attack, whether the IBR is under attack, this model predicts 4 corrected error signals. And to ensure that the predictions of the model do not exceed the stability range of the IBR, only non-attack grid transients are used to train the mitigation models. This shows the performance of the IBR1 mitigation model with each training epoch. We selected an epoch for each IBR that had low MSC but was not overfit. This image here shows our implementation of the network in the loop test bed. So we have a simulation PSCAD running the power system layer, and the co-simulation code running alongside the power system simulation is integrated with TCP/IP client code. We have a Raspberry Pi server that runs TCP/IP code, and the 2 computers exchange data over the network switch. A third computer, a malicious Raspberry Pi, launches cyber attacks on the network switch. This first case shows a denial of service or DOS attack. In this case, attackers are continuously monitoring packets sent in the Area 1 local network. During a transient caused by a set point change on all inverters in Area 1, the attackers launch a DOS attack and disrupt all communication among the inverters in the network. As a result, the IBRs are no longer receiving new data from the other IBRs, and they have to continue using the last values they received after the transient. In this case, these values are severe and cause overvoltage on the outputs of the inverters. With our proposed method, we detect the attack 6 milliseconds after its start and restore the voltage to its expected value, preventing undervoltage. The second case shows a negative 0.3 per unit step attack launched on the reactive power error inputs of IBR1 at 0.1 seconds. This results in undervoltage at the output of IBR1, as you can see in this plot here. But with our proposed method, we detect the attack in 12 milliseconds and restore the voltage about 60 milliseconds later. In this third case, we have a 0.2 per unit ramp attack applied to the real power error outputs of IBRs 12 and 14. We also apply a 0.2 per unit step attack to the reactive power error outputs at the same time. As a result, you can see that IBR13's voltage rises to 1.04 per unit. But with our method, we detect the attack in 16 milliseconds and restore the voltage to normal. This last case shows a random attack signal applied to the real and reactive power error outputs of IBRs 1, 2, and 4. So the attack signal is a random signal following a Bernoulli distribution. At each time step, it is either 0 or 1 with a 50% chance of being either. This results in an overvoltage on the output of IBR1, as you can see in the plot, but our method detects the attack in 120 milliseconds and restores the voltage to its pre-attack value. Our method also reduces the frequency violation in the power system. In conclusion, in this work, we've proposed a model-free cyber-resilient C-space algorithm. Our method is able to successfully detect and mitigate a variety of attack types, including denial of service or DOS attacks, and false data injection or FDI attacks on the C-grade 14 bus North American microgrid. We also develop a network in the loop test bed using a computer running PSCAD, a network switch, and 2 Raspberry Pi computers. This is used to demonstrate both the feasibility of our attacks and the validity of our proposed method. Thank you so much.